Okay, let's dive straight into this explainer today, where we are going to adopt a photographer's mindset to perfectly frame your Cambridge computer science exam answers. Think about this for a second. Have you ever looked at a really beautiful photograph, but the actual subject you're supposed to be looking at is just slightly out of focus? I mean, the lighting is fantastic, the background scenery is there, but that core element is just blurry. Well, believe it or not, that exact same thing happens every single day in Cambridge computer science exams. We're talking across all the major syllabuses, 0417, 0478, 2210, and even right up to the advanced 9618 level. You've probably got all this incredible, rich, theoretical knowledge floating around in your head. But when you actually put pen to paper, the examiner just can't quite see the crisp, clear point you're trying to make. The focus is completely off. So today, we're going to fix that lens. We are going to look at vector graphics, but we're not just looking at it as an isolated topic you need to cram. We're using it as our specific lens to master the art of the perfectly framed exam answer.
Now, the core problem staring right back at us, and honestly, this is a real head-scratcher for a lot of teachers, is this. Why do straight A students still lose marks on vector graphics questions? Think about it. These are the students who literally know the textbook inside and out. They know exactly what a vector is. They know exactly what a bitmap is. But when they actually sit down in the exam hall, they write these super generic, blurry answers that just totally fail to score. They end up writing down a whole bunch of raw computer science facts, kind of just hoping that the examiner is going to sift through all that noise and magically find the right answer. But here's the reality check. In Cambridge exams, examiners do not do that. They don't have the time, and it's not their job. They want specificity. They want to see that you truly understand how a theoretical concept applies to a real-world dynamic scenario. Because if your answer could theoretically apply to any generic question, there is absolutely no way it's going to get full marks on a scenario-based question. It's just not going to happen.
So, to fix this focus issue, here is our 5-step masterclass for today's explainer. 1. Framing the perfect answer. 2. Vector graphics core theory. 3. Where students lose marks. 4. The 3-pass strategy. And finally, 5. Your final exam checklist. All right, let's jump right into section 1. Framing the perfect answer. Finding your subject. Finding your subject is all about decoding exactly what the command word and the scenario are actually demanding of you. Let's really break this down. Are you being asked to identify, to describe, to explain, or to evaluate? Because each of these requires a completely different focal length. If you start explaining when you're only supposed to identify, you are just burning precious time. And if you identify when you're supposed to evaluate, you are leaving massive marks on the table. This comparison right here brilliantly illustrates the difference. Let's look at 2 hypothetical students. First up, we have Alex. Now, Alex overloads the page with raw facts. If the exam question asks about a school implementing a new logo using vector graphics, Alex writes something like, vector graphics use mathematical formulas. They do not use pixels. They are smaller in file size. Now, stop and ask yourself, are those facts true? Yes, absolutely. But are they scoring maximum marks? No way. It's a blurry photo. There is zero analysis linking it to the school. Then we have Sam. Now, Sam isn't perfect. Sometimes Sam rushes and misses the command word. But when Sam slows down and applies the right framework, the answer looks like this. Because the school needs to display the logo on both large outdoor banners and small smartphone screens, vector graphics are ideal as they rely on mathematical coordinates rather than a fixed grid of pixels. This ensures the logo scales infinitely without losing quality or becoming pixelated. Do you see the massive difference there? Sam doesn't just list terminology. Sam connects the precise terminology directly to the provided scenario of the school. So the absolutely crucial takeaway here is that to be like the best version of Sam, you need to follow a strict technical methodology. We often call this the PEAL framework: point, evidence, explanation, link. But let's actually break that down into 4 actionable steps specifically for computer science. Step 1, identify the exact requirement from the command word. Step 2, classify the relevant data or hardware. Are we talking about storage? Are we talking about memory or processing? Step 3, explain the process sequentially. I want you to think of this almost like writing an algorithm. Step A must logically lead to step B. And finally, step 4, connect to context. This is the link part of PEAL. You have to anchor everything you just said back to the school, the factory robot, the office network, or whatever specific scenario the examiner has handed you. Before we continue and reveal the rest of this strategy, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Moving right along to Section 2, Vector Graphics Core Theory, anchoring the definitions. Okay, a really strong foundation begins with clarifying the real-world digital problem that vector graphics actually solve.
We cannot apply that amazing Peel framework we just talked about if our core theory is shaky. To really master how we define vector graphics, you can't just memorize the name or recite a one-line definition you read 5 minutes before the exam. You must distinguish the theoretical foundation from nearby concepts. That is how the terminology becomes actually meaningful. Vector graphics are fundamentally defined by mathematical equations. We're talking lines, curves, shapes, and polygons. They are absolutely not defined by a grid of colored squares. That nearby concept, that's a raster or a bitmap graphic. In computer science, some of the biggest mistakes arise when learners confuse these nearby concepts. You see it all the time. It's the exact same trap as when students confuse memory and storage, or when they mix up validation and verification. If your definition of a vector graphic doesn't explicitly highlight how it fundamentally differs from a bitmap in the way it's processed and stored, your foundation just isn't strong enough to handle a tough exam scenario. So whenever you sit down to study vector graphics, or honestly any topic in the data representation chapter, you must habitually ask yourself these 3 core questions. First, what digital problem does it solve? Well, in this case, it solves the problem of resolution dependency. Think about it. If I take a tiny bitmap picture and try to blow it up to the size of a massive highway billboard, it's going to look terrible. It looks like a staircase of blurry, stretched out blocks. A vector graphic, however, recalculates the math so the line stays perfectly crisp no matter the size. Second, what data is involved? For vectors, we're talking coordinates, stroke width, fill color, and mathematical object properties. And third, what practical consequence follows for a user, a system, or an organization? The consequence is smaller file sizes for simple graphics, infinite scalability, and the ability to easily modify individual elements without ruining the whole image. When you train your brain to think like this, you are quite literally automatically generating the explanation and link parts of your Peel framework.
Let's jump into section 3, where students lose marks, losing the light.
Let's do a deep dive error analysis based on classic, real-world examiner feedback. Trust me, examiner-style performance depends entirely on specificity. Take a look at these common slips that we see year after year. First off, you will lose marks if your answer contains vague wording. Writing down "it's better quality" means literally nothing in computer science. Quality in what way? Are we talking resolution? Are we talking color depth? You have to be specific. Next, you will lose marks for missing process steps. If an exam question asks how a vector graphic is rendered on a screen, and your answer jumps straight from "it uses a math equation" to "there's a picture on the monitor," you have entirely skipped the actual processing steps in between. And here is a massive one, giving advantages with no reasons. Stating vector graphics have smaller file sizes is just an isolated claim. Examiners hate that. But stating vector graphics often have smaller file sizes because they only need to store the mathematical properties of the shapes rather than storing the color data for every single individual pixel on a screen. Now that is a fully explained top-tier advantage. I want you to look really closely at this comparison. This is a classic find the flaw exercise. The flawed response simply says, vector graphics are scalable. That's our friend Alex again, just stating a raw fact. Yes, it's true, but it is completely generic. It could belong to any exam paper in the world. Now, look at the perfected response. In the context of the school's website logo, vector graphics allow infinite scaling without pixelation, ensuring crisp display on both smartphones and desktop monitors. Do you see how incredibly well that hits the target? If the context provided in the question is a school, or an office, or a robot, or a commercial website, your answer absolutely must stay explicitly inside that context to get full credit. We explicitly mention the school's website. We mention the specific hardware involved, smartphones and desktop monitors. We clearly explained the real-world effect of scalability, which is avoiding pixelation. That right there is what a perfectly framed answer looks like. So here is what I want you to do. Mentally pause before you write a single word of your next exam answer and ask yourself, what exactly is this specific task testing? Is it testing a process explanation, like the step-by-step of how the graphic is actually drawn? Is it testing logical reasoning, like why an IT manager would choose a vector over a bitmap for a specific company's marketing? Or is it testing an evaluation of a method? Once you accurately diagnose the demand, you stop yourself from just word vomiting everything you memorized onto the page. Instead, you write a beautifully targeted, laser-focused response. Stop scrolling. Subscribe to our YouTube channel, Ace the Exams at @AceTheExams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @AceTheExams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions.
All right, let's roll into section 4, the 3-pass strategy, adjusting the lens. Now that we know exactly where students slip up and we understand how examiners think, let's introduce a reliable, repeatable correction strategy. Think of this as your personal computer science success blueprint. It's like manually adjusting the lens of your camera until the image is perfectly, brilliantly sharp. This 3-pass revision cycle is exactly how you should be studying for rigorous subjects like 0478 or 2210. Pass 1 is where you secure your key definitions and contrasts. You ensure you know precisely what a vector is and, crucially, how it directly contrasts with a bitmap. Pass 2 is where you rehearse worked explanations. You don't just sit there memorizing facts, you physically practice writing out full paragraphs using that Peel framework. You rehearse the diagrams. You rehearse how the math actually translates to shapes on a monitor. And Pass 3? Well, this is the master level. You focus entirely on exam adaptability. You take a past paper question about a school, and you mentally change the scenario to a robotics factory or maybe a smartphone app developer. Then you ask yourself, how does my answer need to change? Testing your adaptability by changing the scenario is the ultimate proof that you actually understand the concept, rather than just memorizing a mark scheme. When you practice your speed writing, and by the way, I highly recommend giving yourself strict 30-second or 60-second timers to write out a perfect Peel paragraph at home, always frame your paragraphs using these 4 highly reliable memory prompts. 1. What is it? Define the concept clearly and accurately. 2. How does it work? Explain the underlying technical process or the technology itself. 3. Where is it used? Link it explicitly to the specific scenario given in the exam prompt. And 4. Why is it chosen? Justify it over an alternative, like explaining exactly why vector is chosen over bitmap for a corporate logo. If you consistently hit these 4 prompts, you will literally never leave out crucial evidence, and you will naturally hit every single assessment objective those Cambridge examiners are desperately looking for. And finally, section 5, your final exam checklist, the final print. Okay, we've set up the shot, we've taken the photo, we've developed it in the darkroom, and now we are looking at the final print. Let's put together the complete answering system to guarantee those top marks before you ever walk into that exam hall. This checklist you're seeing right now is your absolute ultimate tool. You should have this mental table checked off before you even think about moving to the next question on your paper. Did you diagnose the demand? Yes or no? Did you actually answer the specific command word they asked? Did you anchor the context? Is there actual evidence in your paragraph that links directly back to the scenario provided? Or could your answer apply to literally anything? Did you sequence the process? Did you explain how it works, step by step, logically, without skipping the vital middle parts? And did you justify your choice? Did you explain why this specific technology is the best fit? Very often by contrasting it with what it isn't. Use this strictly to ensure you haven't just described a piece of technology that vaguely sounds related, but have actually answered the very specific question sitting right in front of you. And guys, this brings us to an absolutely incredible piece of data. Students who actually take the time to implement these specific computer science strategies see an average improvement of 2 whole grade boundaries. 2. That is literally the difference between getting a C and getting an A, or jumping from a B straight to an A star. By consistently applying this specific framework, actively decoding the command words, and rigorously anchoring your reasoning to the provided scenarios, you instantly stop throwing away easy marks. But of course, there's a catch. This only works if you actually practice consistently with our weekly explainers. So here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at @AceTheExams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @AceTheExams_IGCSE and click that bell. Don't let another exam pass you by. I want you to drop a comment below with your target grade for computer science and tell us the biggest challenge you're currently facing. Our team actually responds to every single comment. And hey, make sure to like and share this explainer with a study partner who needs it. Ace the Exams, your Cambridge success starts here. So I'll leave you with this final thought. By consciously applying the photographer's mindset to your computer science exams, you can absolutely guarantee clarity, precision, and depth in every single response. You already have the theory in your head. Now you finally have the right lens to focus it. So when you walk into that exam hall, when you sit down at that desk, open that paper, and uncap your pen, is your next answer going to be a blurry snapshot, or are you going to frame a masterpiece? Keep practicing, stay focused, and we will see you in the next explainer.